Welcome to our fifth lesson on work, power and energy. We'll be looking at a typical exam question today on forces and work. Now our question starts off by telling us that Lwandile applies a force of F to help his friend in a wheelchair to move up a ramp of length 10 meters and a vertical height of 2 meters. Further on they told us the combined mass of his friend and the wheelchair is 100 kilograms and the frictional force between the wheelchair and the surface is 20 newtons. The wheelchair also moves up the ramp at a constant velocity. Now, a very important part of the question is the fact that it is moving up the ramp at a constant velocity. But the first question would ask us to draw a free body diagram to indicate all the forces acting on the wheelchair. Now, sometimes they might not even ask you to draw a free body diagram and just continue straight to the questions. Now, it's very important though for yourself that you do draw a free body diagram. Now, when drawing our free body diagram, we see the object as a dot. Normal force will be working onto it as it's on the surface, but this normal force acts 90 degrees to the surface. They did tell us that there is friction involved, and if the object is then moving up the ramp, as the applied force by Lwandile is, then note that friction is actually then working opposite to that, which would be down the ramp. Also, there is gravity involved. Now, gravity works straight down, but if gravity works straight down, then we can break it up into components because this then acts at an angle. Now, it's always best to rather go and break Fg up into its two components than drawing Fg. Now, note there's always two components for Fg, and those components act 90 degrees to each other. It's known as Fg perpendicular and Fg parallel. Note, because this object is then having a force gravity that pulls it down, that the two components will still be pulling it down. We won't have Fg parallel now working up the slope. Remember, it's got nothing to do with the applied force, it's all about the direction of gravity. So when doing your free body diagram, you can pick either one of these two to draw, but it's best, even if you decided to draw the first one, to draw the second one for yourself at least, so that you can look at all the forces working parallel to the displacement. Now the second question goes on by asking us, what is the magnitude of the net force acting on the wheelchair as it moves up the ramp? Now let us look again at our free body diagram. It's important again to take in consideration that this object was moving at a constant velocity, as was stated in the question. Usually if you come across a word like this, it's important to highlight or underline it, because that's going to determine the rest of the question. Now, constant velocity means that all the forces working in forward direction of motion must be equal to all the forces working in a backward direction of motion. So my motion though is up the slope, which means parallel to that I've got the applied force. But opposite to that, still parallel, is friction and Fg parallel. And if this is constant velocity, then it means all the forces up the slope is equal to all our forces down the slope. And at constant velocity, therefore, we do not have a net force. Remember, net force means the overall effect, and if they're both equal, then there is no overall effect. They'll cancel each other out completely, and therefore F net is 0. And in order to explain, you'll say because it's traveling at a constant velocity. Do also take note that if something is F net of 0 and a constant velocity, it will also mean that the acceleration of the object is 0. That means it's not going faster or slower. It further on asks us what is the magnitude of the net work done on the wheelchair on reaching the top of the ramp. Now if you can remember, we said if we want to go and calculate work net, and we're using our formula of force and displacement, then we need to use the net force in the calculation, because it always goes hand in hand when it comes to subscripts. So if my force net, as was said in my previous question, is 0, then everything multiplied by 0 is going to end up giving me 0. So that means the work net done would also be 0. Now the last question asks us to go and calculate the work done on the wheelchair by Lwandile. Now first off, let's again go back to our free body diagram. Remember we said because he's traveling at a constant velocity, it means the applied force is equal to the frictional force and Fg parallel added up together going down the slope. Now if we need to go and calculate the work done on the wheelchair by Lwandile, then it means we're talking about the applied force that we need to go and calculate, that force work. Now first off, our formula would start off by saying work due to the applied force is equal to the applied force times delta x times cos of theta. But there's a few hiccups. First off, we do not have the applied force. We'll need to go and calculate it. Now if I go and look, we said the applied force, because F net is 0, it means that F applied minus Fg parallel minus friction is giving us 0, and that means my F applied is thus equal to Fg parallel plus friction. Okay, so I can go and find F applied. I just need to add up my Fg parallel and friction. I've got the value for friction, which is 20 newtons, but I do not have Fg parallel. Now Fg parallel you can always go and calculate making use of sine theta multiplied by Fg. And remember, Fg in this case is the hypotenuse, but we can also further on go and calculate it by saying mass times gravitational acceleration. So we would first need to go and calculate my Fg parallel. From there onwards we will be able to calculate F applied. But it's not the only unknown in our formula. We still need to go and calculate our theta angle as well, because the only thing that they've given us was the sides of this specific triangle. So when looking at calculating Fg parallel, we would realize, yes, that we still need that theta angle, and if we go back to what was given to us, the length to be 10 meters and the specific side that is opposite to the angles to be 2 meters. So in order for us to go and calculate the angle, we'll be making use of sine theta. So sine theta is thus 2 meters divided by the 10, and that will give us 0,2, but we'll need to go and do the second function of sine to determine the angle from that still. Now this angle will do not round off to 2 decimal places because it's not my final answer. So we'll keep it with all its decimal places. It's 11,536 and a few decimal places degrees. Now when we do our calculation now for Fg parallel, we'll then say sine of this 11,536 degrees with all its decimal places, multiply the mass of the friend and the wheelchair, which was given as 100, multiply by 9,8, and this ends up giving us 196 newtons. Now from here onwards we can go and calculate F applied. Remember we said now because F net being equal to 0, F applied will be equal to Fg parallel plus friction. Now if our Fg parallel was 196, friction was given as 20, so therefore this ends up being 216 newtons for F applied. So looking at the work due to the applied force, we've now calculated the applied force to be 116. The distance which it had to cover was 10 meters up the slope, and now very important, if we go back to our free body diagram, our applied force was moving up the slope. And also note that the motion of the object was also up the slope. And therefore, because they're going in the same direction, our angle between the two force and the motion is cos of 0 degrees. And this then ends up giving us 260 joules. So that is the work done due to Lwandile's applied force.